If I went into the math of how how much it distorts, yeah, more math sophistication would help. How much it distorts depends upon the speed. So if the closer you get to the speed of light, the closer the prime axes get to each other. And if it's going away, then they would distort the other way. Other questions?
Other than math, have we ever been able to like even attempt to do this? And I mean, theoretically, like attempt something like this.
You mean experimentally?
Yeah,
I mean, the muon experiment was done,
which is can prove this.
which gives pretty good evidence that this works. Another place where this actually is used in more everyday life, GPS brings this into account. Actually, it brings general relativity to warping because of the mass of the Earth, and as well as it's traveling at, the satellites are traveling at a couple thousand miles or meters per second, which doesn't have a huge effect, but it's enough to throw a GPS off by, is it 10 meters a day? Somewhere in that order of magnitude.
So they do have to.
Yeah, they do have to take that into account.
You said something earlier, ignoring the effects of being close to the pole. What would happen if you were in the barn around the pole moving that fast?
What would our perspective be? Like if there was a third perspective.
Wait, say that one again?
If you were in the barn, say like a meter from the pole, as it zooms past you, would you be able to survive that if the pole was moving that fast?
If the pole were actually moving that fast, bringing reality into it, I would assume that it would be, basically the air molecules would not be able to move out of the wave time. And so it would be smashing the air molecules into each other, creating ultimately a nuclear explosion.
So short story, yes, you could. Just again.
You would not notice.
It'd be it.
That's based upon Randall Munroe's analysis of throwing a baseball near the speed of light. What would happen?
Oh, so if anything moves that fast and all the air molecules smash into each other, it would create.
As you smash particles into each other. Yeah, if you can fuse nuclei into another nucleus. Well, you either split it, or if you split it, you got fission. And so you got the atomic bomb. If they merge, you get fusion, and you get the hydrogen bomb.
Either way.
I think it's fusion that would occur.
Either way, it wouldn't be good.
No, probably not. Hopefully they would film it so that we'd be able to use it as a lesson for future generations.
Don't go to baseball really long.
If you're not familiar with What If, I'm sure I've mentioned it before, but Randall Munroe does I'm pretty sure there's a podcast. He's written a couple of books. It's basically serious scientific answers to ridiculous questions. Highly recommended.
This is why we can't play dodgeball anymore.
Afraid of nuclear explosions? Yeah. Sorry, seeing notes here of all the letters that are used in physics. I was thinking of an alphabet song for your kids based upon physics. Z is for impedance, X is for reactance. All right, so let's take a look at one other this concept of, since we're showing that there's not a whole lot at the same time is different, is there anything that is actually the same for both, no matter what the reference frame is? Well, we've established one. speed of light. But is there anything else besides the speed of light that is going to be the same for both groups?
I don't know if this is right, but distance, like does the distance change depending on your perspective?
Does what change?
Distance, or, yeah.
Depending upon your perspective, if
Like, even still, if I'm the pole, the barn is 10 meters away, and I'm the barn, the pole is 10 meters away from me. Does that change?
oh, what the barn sees as you being 10 meters away would not be what you would consider being 10 meters away.
Okay.
Because that would be as if we had another event 0. So from the barn's point of view, the position is negative 10 meters. The time would be, I guess, probably negative 7.7 nanoseconds. No, it would be more than that. It'd be some, whatever time it is. And then you pop them into those equations, you would not get the same number. All right, so let's go back to the original thought experiment that we did with this, the box in the mirror. So we had the box that was zipping along at some speed v. This distance here was h. And so the light goes there and then back. And then over here, from the box's point of view, it just goes up and down. We're going to do a third scenario here where it's not going as fast as it is in this particular scenario. So here v is equal to 0, here is v is equal to whatever it is. And then in a different frame, what do we call this? The h double prime frame. That's this legal, let's just call it frame 1, frame 2, and frame 3. It's traveling at some speed v. This distance still here is h. We'll call it v3, v1, v2. So in this scenario, we do have something in common to all three reference frames, besides the speed of light. And what is it? Say it again.
Is it H?
It is indeed h. So let's take a look at what h is equal to, and look just the first and the third frame here. I know that this distance from here to here is going to be v1 t1, whatever that time is in that reference frame. Over here, this distance from here to here is going to be v3 t3. Looking at my triangle right here, that this is h, this is v, this is 1/2 v1 t1, and then my hypotenuse would be the square root of h squared plus, actually, not the way you want to do that. And this distance right here would be 1/2 t1. Because the light is traveling that whole distance, and so ct1 would be the total distance it travels, and it's doing half of that. So I have h squared is equal to 1/2 ct1 squared minus 1/2 v1 t1 squared. If I did the same thing down here, I would get h squared is equal to 1/2 ct3 squared minus 1/2 v3 t3 squared. So I seem to have this relationship here that, well, let's simplify it some. Let's just multiply everything through by 4. So I get 4h squared is equal to c t1 squared minus v1 t1 squared. Same here except for the subscript 3. So I seem to have this value regardless of what reference frame I'm in, that the speed of light times time squared, c squared t squared, minus the speed of the object squared t squared is a constant.
Why'd you do 4 instead of just 2?
It's 1/2 squared.
Oh.
We can take it one step farther. Vt is just how far the box travels, so that is sort of a position. So this can then morph into c squared t squared minus the distance traveled squared is equal to some constant. Now 4h squared, but it doesn't really matter what h is. But we have this other thing that's common, so the speed of light is common to everything, is the same for everything, and this relationship here between the reference frames is the same for everything. I'm going to skip that derivation. You're welcome. Now, there is one other bit that was alluded to yesterday. Nope, I'm going to do one other thing first before I get to that illusion. Illusion, not illusion.
Sorry, one more question.
Yeah.
That is c squared t squared minus k to the x squared equals something
Constant,
constant.
or cons, period.
That's
So we've talked about comparison between the two reference frames in terms of position and time. What about velocities? So if you're in a rocket ship and you are throwing a relativistic baseball in a vacuum, presumably, otherwise the rocket ship would be no more. So if the rocket ship relative to Earth, so the speed of the rocket ship relative to Earth is, I'll make it velocity, is equal to 0.8 times the speed of light. And the velocity of the ball with respect to the rocket is 0.7 times the speed of light. So from his point of view, the ball's going to be going 0.7 times the speed of light. From Earth's point of view, the rocket's going 0.8 times the speed of light. How fast is the ball going with respect to Earth? Pardon?
Is it the same as the rocket? 0.8?
No, it is not the same as the rocket. So let's put this in terms of Galilean relativity. You're in a car? Car. Scion XP. So the car is going, so the velocity of the car with respect to the Earth is 50 meters per second. Yes, I know, completely unrealistic for that type of car. And somebody in the back seat is throwing something forward, and so the velocity of, let's just say it's a ball, with respect to the car is going at 10 meters per second. Then the velocity of the ball with respect to the Earth would be
10 meters per second.
Go.
60
Yes. Do the whole thing.
meters per second.
Yeah. When you're adding vectors, when you're doing relative summation like this, velocity of A with respect to B is going to be the velocity of A with respect to some other thing plus the velocity of C with respect to B. As long as those are the same, it's valid. Those are the same, and that's those letters are the same, those letters are the same. So the velocity of the ball with respect to the earth would be the velocity of the ball with respect to the car plus the velocity of the car with respect to the earth. So 10 plus 50. If we apply that over here, hopefully you can see that we violated a law of physics, because the velocity of the ball with respect to the earth would be the velocity of the ball with respect to the rocket plus the velocity of the rocket with respect to the earth. So if Galilean relativity were true, then this would be 0.7 times the speed of light plus 0.8 times the speed of light, which is 1.5 times the speed of light. Which physics is saying no, not happening. So we need to somehow be able to add these. Yes, it's a need. We need to be able to. So what we're going to do is do a classic drawing. We're going to call this frame S. Frame S prime. S prime has a velocity with respect to S, so the velocity of S prime with respect to S is, well, just to keep it in sync with my notes, I'm going to call that U, just so I don't have to deal with subscripts. Now in this prime frame S, well, within S prime frame, I have an object that is going to be moving. So I have a separate object here that is moving with respect to S, and so the velocity, and what do I call this, just particle P. So the velocity of P with respect to S prime is, again, keeping sync with my notes, we'll call W. And what I want to know is what is the velocity of the particle with respect to S. So this would be related to that Earth, rocket ship, ball being thrown. So why don't we just say that the ball of the particle with respect to S is V. So I need to know the relationship between V and U and W. I know that if Galilean relativity works, so Galilean, then V equals U plus W, but that has issues as we pointed out over there. All right. So if a particle is moving at some velocity W, again, when I'm in the S prime frame, that should be the distance that happens in the X prime frame over the time in the S prime frame. Speed is distance over time. It's only traveling in one direction, that's why I'm flipping back and forth between velocity and speed. If I wanted to relate it to the S frame, I got my Lorentz transformations that we've done. Well, you tell me, what's X prime equal to in terms of position and time in the S, in the non-prime frame?
Gamma times x minus vt.
And time frame, T prime?
Gamma times time minus
C, isn't it, or Vx over C squared?
Yeah. Gammas cancel out. So we're left with that. At this point, I wanted to multiply top and bottom by 1 over t. So I get x over t minus v, and on the bottom, 1 minus v over t. Actually, v over c squared x over t. So x and t are the distance and the time in the non-prime frame, and just the s frame. So that would just be the speed v. Oop, lost something in there. So x minus vt. Oh. Need to make one small adjustment here. What Ethan said was right. However, this should be how fast s prime is going with respect to s, which we've defined as u. There should be a u there. And so, there we go. So x over t is how fast it's going in the s frame, so that's just v minus u over 1 minus u v over c squared. So looking at the relationship here, sort of adjust this a little bit. We have w is equal to v minus u in the Galilean frame, and that's our numerator, but we have this denominator to keep it from going over the speed of light. So that's w. So relativistic velocity addition, you get this. If we're not dealing with relativity, it would be that. So let's plug and chug, figure out how fast it would be going with respect to Earth. W equals. So v, that's the speed of the particle. Well, that's what we're trying to find. So if I want to do it in the just simplify it. Dot dot dot. We have v equals u plus w over there, so relativistically it'd be v equals u plus w over 1 plus u w over c squared. Once you have established the Galilean one, the relativistic one follows the pattern. And so we end up with the speed of the ball with respect to Earth.